and gentlemen, please welcome NVIDIA Fellow, David Kirk.
Good morning and welcome to GTC Japan and the Graphics Technology Conference, GPU Technology Conference in Tokyo. And I always love coming here to speak because there's such enthusiasm for technology. I really feel at home, like you embrace everything we do. So thank you for welcoming me here. The GPU Technology Conference was born by the invention of CUDA and the invention of GPU computing. And we're really inspired by the fact that graphics is more than just a pipeline. Graphics is computational, and visual computing is broader than just making pictures. You start with physical simulations, parallel computation, and a lot of math and a lot of understanding, and you build the pictures and you build solutions along with the pictures. GPU computing has experienced exponential growth. CUDA is the realization of two kinds of computer processors working together. The CPU is a high-speed, serial, single-threaded processor. Low latency, can process a small amount of information very quickly. The GPU is a highly parallel, high-throughput processor, many threads, many pieces of data, lots of things happening at the same time. So the marriage of these two kinds of processors enabled by the CUDA programming environment allows us to achieve many exciting and interesting things. GTC Japan has been growing and evolving. The first GTC Japan in 2010 had just under 500 attendees. Today, I think we have more than 1,500, actually over 1,600 registrations, and maybe we'll have even more attendees than that. The mix of attendees and participation has changed over time. We have now very broad industry participation, a lot of different companies contributing, sponsoring, and attending. And the kind of applications and the kind of problems that we look at have changed through the course of multiple GTCs. Today we will talk quite a bit about computer vision, using machines to recognize and analyze things, as well as machine learning, teaching computers to understand, analyze, and extract information from images and other data. As we have an explosion of imagery and other data that is being captured and uploaded to the internet, we have to figure out what to do with it, analyze it, and it's just too much raw data for people to analyze, so we need to have the machines help us. Since its introduction, CUDA has really blossomed and expanded, and we say CUDA everywhere, and we mean it. We want CUDA on every kind of device, from embedded devices in vehicles and other kind of objects, phones, tablets, computers, supercomputers, every place. We have over 500 million CUDA-enabled GPUs that have been shipped. A very large number of CUDA downloads, which indicates the size of the developer community. We teach CUDA in parallel programming courses worldwide. Probably by the end of this year, early next year, we'll be close to 1,000 university courses teaching CUDA. And that leads to new applications, new exciting ways of using GPU computing, academic papers, research, and real products, real technology that makes use of CUDA. So I'll just highlight a few examples of things that have been done that we think are particularly interesting. There's a company called Rescue, I believe they're in Australia, that has been exploring using GPU computing to enhance the capability of drones or unmanned aerial vehicles. Onboard GPUs are used to do navigation and collision detection so that you can have more drones up in the air looking for forest fires and doing surveillance for people's safety without colliding with the other drones that are in the air at the same time. At University of Illinois, on the Blue Waters supercomputer, there were over 3,000 GPUs applied to the problem of simulating the capsid of the HIV/AIDS virus to try and understand the infection mechanism and be able to potentially defeat it. If you can understand how the capsid works, you can prevent it from being allowed into the cells and infecting cells. That simulation involved simulating over 3 million atoms in the molecule. I think it's a truly amazing achievement. Another company, Hologic, is using GPU computing to do 3D reconstruction of imaging data for breast imaging to do a better job than simply using X-rays for identifying a disease or tumor tissue. So this results in much lower radiation doses and much better quality detection and much better quality healthcare. The GPUs are changing people's lives in all these ways. Closer to home, work that's going on in Japan. Tokyo Institute of Technology, there is a project that is using parallel GPU computing to identify substrings or K-mers in DNA sequences to try and determine the frequency of particular patterns. And this can be done much more efficiently with GPUs and CUDA. At Waseda University, they're using GPUs to teach robots how to select appropriate behaviors. They use a deep neural network and use GPUs to train the network and to figure out grasping motions, how the robot should behave. Hokkaido University has a project where they use parallel finite element model simulation to simulate the deformation and fracture or tearing of soft biological tissue, to simulate surgery and provide training, haptic feedback for new surgeons to be able to learn how to do surgery without actually cutting real flesh. So these are very exciting applications, and these are examples of GPUs really changing what we're able to do. One recent announcement at the International Supercomputing Conference a couple weeks ago shows the reach of GPU computing. Several companies have announced that they're going to build ARM64-based servers for high-performance computing. And this is really significant because traditionally, other CPUs have been used as the core processors for high-performance computing. And ARM64 is a much more lightweight kind of CPU architecture, much more power efficient than some of the processors that have been used before. But by itself, ARM64 would not be sufficiently powerful as far as computing to really build a supercomputer. But the combination of CUDA with GPU computing combined with ARM64 CPUs provides an excellent power-efficient substrate for building next generation of high-performance computing. It's certainly not the only way to build these, but it's a new innovation. It's a new approach to building high-efficiency, high-performance computers. Other approaches to power-efficient supercomputing. The Green 500 measures the most power-efficient implementations for supercomputers, and all of the top 15 winners in the last round that was announced have NVIDIA GPUs in them. In fact, they have Kepler architecture GPUs, and again, number one is very, very close to home. The Tsubame KFC supercomputer, which is at Tokyo Institute of Technology. I just found out yesterday that KFC stands for Kepler Fluid Cooling, not the Kentucky deep-fried chicken that you might associate with KFC. But the name is appropriate because it is the processors are immersed in oil to manage the thermal cooling for the computer. So the processors run at a very reasonable, much lower temperature than in an air-cooled or water-cooled system, and so you get more power efficiency. I think it's a really great machine, and maybe the wave of the future for supercomputing. We may see a lot more oil-cooled systems. So the other implication of Kepler, besides moving up the computing food chain into supercomputing, Kepler has also moved down into our mobile architecture. You may or may not know, historically, our mobile architecture, the Tegra family of processors, had a different graphics pipeline than our GPUs for desktop and high-performance computing and laptop. The progression of architectures for the desktop, from Tesla to Fermi to Kepler and on to Maxwell, is our fully capable, fully functional, does all of graphics, does all of computational graphics, supports CUDA. With the introduction of our Tegra K1 mobile processor, we've now unified our architectures. So going forward, we'll be building a single graphics architecture which spans the full gamut from mobile and embedded architecture all the way up to HPC. And what that really means is that all the capabilities from programmable graphics, visual computing, all the way up to CUDA and programmable parallel computing are available from embedded architectures to be deployed and developed all the way up to very high end. So now I'd like to demonstrate the truly awesome power of Tegra K1. If we can switch to the demo.
You want to play?
So that's a truly amazing quality of graphics for a mobile device. Let's take a little drive through here, explore the environment, see the nice quality reflections of the water, the damp floor. You see the indirect lighting and special effects, the God rays in the background, the light shining through the atmosphere. So really, this is virtually indistinguishable from the desktop gaming experience, truly capable. And this is all running on Tegra K1 development platform, running under Android. We pull up the Android menu here. So you can see it's fully integrated with Android. So this is very exciting. Thank you very much. Let's go back to the slides. Okay, so Tegra K1 allows a whole bunch of new experiences for handheld and embedded devices. Besides gaming, which I've just shown you, Tegra K1 was all over the recent Google I/O conference. I showed you the gaming, which is part of the new gaming environment on Android. We're also very involved with Android TV, computer vision on a tablet, the Tango project where you can capture 3D information with a tablet. We're in Chromebooks. We're the first Android Auto platform, and we're also the first development platform for 64-bit ARM with Android, the Android L release. So we're really enabling a great breadth of GPU computing on Android everywhere at Google I/O. So this is a truly impressive platform, and we've built a truly amazing development vehicle for it. Jetson TK1 is what we call the first mobile supercomputer for embedded systems. We have Tegra K1 on it, and all the other peripheral connectors, memory, and all the other pieces, so that you have a fully functional computer on a board. So it's a mobile supercomputer. This has 192 CUDA cores. CUDA 6.5 offers support for ARM and development, a bunch of tools, SDKs, and libraries that allow you to develop applications on this platform. And this is 326 gigaflops on a very small mobile chip. It's really a tremendous achievement. And you can get hands-on experience with this here today. And it's also available in e-tail. You can order one. I don't know the Japanese price, but it's very cost-effective, very excellent entry into GPU computing and development. Okay. So one other topic I'd like to talk a little bit more about is machine learning. And machine learning is a pretty old branch of artificial intelligence, first explored maybe 50 years ago. And the idea is that computers can, on their own, learn from data, from information that you present to them. And the best way to be able to do this is unsupervised learning, where the computer program will go through a whole sequence of training data, for example, images, and figure out what can be recognized from it, figure out different classes of things that it can identify. So just like humans, we're born without the ability to identify and recognize specific kinds of objects or animals, but we learn over time as we experience our life. You want to have a computer program that's doing machine learning be trained on a set of images and learn to recognize a person or a dog or a cat very effectively. This is very hard to do, though. So this is, we're at a very special time in the history of machine learning, because there are a few trends that are converging, things that are happening at the same time. The first one is there's an explosion of data I mentioned that earlier. Just a few years ago, there were approximately 300 million images being uploaded to the internet every day. And today, probably by the end of this year, there'll be close to 2 billion images uploaded per day to the internet. And all of this is just people's pictures, and they're unclassified. You don't know what's in those pictures, but you would like to be able to figure out, recognize faces, recognize people, like recognize objects, like show me a bunch of pictures of cats, for example. There's also study in deep neural networks, which is a approach for machine learning, and the growth of GPU computing, the explosion of parallel pervasive computing. The three of these things together are enabling a real explosion in machine learning. So a while back, Google, in Google Labs, built a project called Google Brain out of 1,000 CPU servers, over 16,000 cores, spent quite a bit of money and quite a bit of power, over $5 million, to build a deep learning system that they were able to train over the course of many weeks to recognize a variety of features in images. So there was considerable excitement about just scaling up to this level and being able to do that. Sometime later, Stanford AI Lab was able to duplicate the performance in terms of recognition quality of Google Brain with a much smaller substrate. So 3 GPU accelerated servers, roughly the same number of cores in 12 GPUs, and about 1/150th of the power and much lower cost. So we really see machine learning becoming pervasive, getting much more broadly applicable. And another example of this is ImageNet, which is a very large collection of images that are commonly used as a baseline for machine learning training. There's a challenge that happens every year where people write their own programs to compete with other people who are trying to demonstrate that they can recognize features in image. And just last year, more than half of the teams competing in this effort were using GPUs. So you can really see that this leverage, this advantage of highly parallel computing is something you can't ignore. It's going to revolutionize machine learning. So you can see this by the fact that many large companies are using machine learning for production, for real products. And there's a lot of important research going on at universities in this area, so the field is moving very, very rapidly. And there's a very broad collection of use cases. I just mentioned the image classification, but pretty much any situation where you have a large volume of complex data and you want to extract some meaning from it, machine learning is going to be the way to proceed. It's the only way we can deal with that scale of data. So I think this is a very exciting development. Next, I'd like to have some presentation about enterprise virtualization, and I will step off the stage. And please welcome Mr. Mark Hamilton, who will talk about this topic.
Welcome, everyone. It really is amazing that we've come this far, as the words in the opening video said. If you think about it, it was only 21 years ago that NVIDIA was founded in 1993 and put the first GPU in a PC on the desktop. And think back to 1993. There's been a lot of change since then. Unless you worked at CERN labs in Switzerland, you probably had no idea in 1993 what the World Wide Web was. And unless you lived in Finland and worked for Nokia, you were still, if you had a cell phone at all, it was an analog cell phone that only did voice. And of course, you had a GPU on the desktop. And David spoke about all the great things that have happened in graphics and in computation. So let's talk a little bit about the changes going on in enterprise virtualization. Enterprise virtualization 2.0, as we call it. Surprisingly, with all those changes in the last 21 years, enterprise virtualization has really focused on the server and has left behind graphics on the desktop. I'm not sure if anyone has ever used VDI, but because traditional enterprise virtualization did not use a GPU, it was not a very good experience. And it wasn't until recently, until all of the great engineers at NVIDIA started to work on our virtual GPU technology, they were really able to make a difference. And for the first time in 21 years, take that GPU off of the desktop for graphics and move it back into the server, where you can have security, you can have it professionally managed, and yet you can still deliver that solution to all the new devices that the enterprise users want to use. Not only PCs, but laptops, tablets, cell phones, and other devices. And as you would expect from NVIDIA, the visual computing company, we really help make it a night and day difference between the virtual desktop without a GPU and the virtual desktop with a GPU. But since we're the visual computing company, I didn't want to just show you a slide. Let's show a quick video that shows a slide-by-slide comparison. So on your left, you see one of our partners, Citrix Zen Desktop. They're the world's leader in desktop virtualization. They're running an application. This is very similar to Google Maps. It's called ArcGlobe. And while you would expect the performance on the right on a low-end laptop, when you virtualize in the data center using only software-based graphics, you get the very poor experience on the left. Again, users have not been happy with this, and not until the NVIDIA virtual GPU in grid technology was adopted by Citrix were they able to deliver the real graphics performance in a VDI or virtual enterprise experience. So a short video is nice. You can actually see that video on YouTube. But if you follow me on Twitter, I did promise this morning that I would make a special announcement. So we wanted to make sure that all of you, when you left, could not just see a video of graphics accelerated VDI. And I expect some of you may want to talk to Citrix and your hardware OEM and actually start a trial in your own company of graphics accelerated VDI. But we wanted to make it even easier for you. And so as you would expect with Enterprise Virtualization 2.0, we took the NVIDIA grid technology and we put it in the public cloud. And starting this week, right here in Tokyo, you can sign up and get a graphics accelerated desktop for 24 hours. So rather than just talk about that, I'd like to invite up my first guest to give a quick demonstration. So please welcome Mr. Masaki Sawai, who's going to come up and give a demo of the grid test drive.
それでは実際にグリッドテストドライブ、見ていきたいと思います。グリッドテストドライブに必要なのはたった2つです。通常のパソコンと、皆さんお使いのパソコンとインターネット回線、その2つです。はい、グリッドテストドライブを使うには3ステップで行います。まずはブラウザを開いていただいて www.nvidia.co.jp/try-grid とアドレスを打っていただくとグリッドテストドライブのウェブページにつながります。こちらでテストドライブをお試しくださいというボタンをクリックしていただくとアカウントの登録画面に移ります。こちらでご登録をお願いします。登録は無料となっております。登録が完了しますと、グリッドワークスペースというソフトウェアをダウンロードすることができます。ダウンロードして PC にインストールしてください。以上でグリッドテストドライブを使う準備が完了しました。それでは実際にグリッドワークスペースを起動してみます。まずはですね、ログイン情報を求められます。こちらはですね、登録で使用した情報を入れてください。私のメールアドレスと設定したパスワードですね。そして、接続先なんですけれども、こちらアジアを選んでいただくと日本の皆様快適にお使いいただけます。そしてサインインのボタンを押しますとパブリッククラウド上で仮想マシンが立ち上がりデスクトップの準備が始まります。しばらくするとこのように、Windows の、画面が出てきますが、こちらがですね、クラウド上で動く Windows の、デスクトップでございます。こちらのデスクトップはですね、NVIDIA グリッドによって GPU アクセラレーションを利用できる環境となっております。そして、このグリッドテストドライブでは、デスクトップ上にですね、あらかじめデモ用のアイコンを用意しております。ダブルクリックしていただければ手軽にグラフィックスのですね、アプリケーションを体験していただくことが可能となっております。いくつか見てみましょう。まずはですね、ウェブブラウザで動く HTML5 のデモでございます。GPU アクセラレーションによって、ウェブブラウザ上でもこのように 3D の表現、可能となっております。はい、本を開いてみるというのも可能ですね。他にもいろいろあります。ですね、こちらのグリッドテストドライブの環境ですけれども、最新のケプラーアーキテクチャですね、ケプラーアーキテクチャの GPU を使うことができます。ですのでこちらのようなですね、ハイエンドのグラフィックスを使ったアプリケーションも問題なく動作できるようになっております。はい、他にも見てみましょう。プロフェッショナル向けのアプリケーションとして CAD のビューアーがいくつかインストールされております。こちらはですね、シーメンスのチームセンターのですね、CAD のビューアーの画面でございます。こちらのようにですね、自由にマウスを使ってインタラクティブにCAD モデルを快適に操作することができて、描画もしっかりと正確に行えているのがお分かりだと思います。もう一つですね、SolidWorks eDrawings も同じですね。こちらも CAD のモデルをですね、このように自由に回転できます。NVIDIA グリッドを使うことでいつでもどこでもそして安全に CAD データを活用できる環境、それをグリッドテストドライブで手軽に体験いただくことが可能となります。はい、そしてですね、こちら、あらかじめ用意されたデータだけなく自分のデータを使いたいという時はですね、こちらの使いたいファイルをグリッドワークスペースのですね、ウィンドウにドラッグ&ドロップするだけで、仮想マシンにですね、データがコピーされて自由に使うことが可能となります。このようにですね、グリッドテストドライブは PC とインターネット環境だけがあればいつでもどこでもですね、グラフィックスを使った仮想デスクトップ体験を可能となります。登録は無料となっておりますし、今現在からお使いいただきますので、ぜひ皆様、一度お試しください。きっと気に入っていただけると思います。ありがとうございます。Thank you, Mark.
Thank you. That was an amazing demo. And once again, it wasn't just a demo running on the laptop here or in a server behind the wall. That was, for the first time in 21 years, the full power of NVIDIA visual computing technology brought to you from a server in the cloud here in Japan and delivered to your desktop. And all of you can go, maybe not all at the same time, but go and sign up today. Less than 2 minutes to sign up, and you can get your own graphics accelerated session. And if your company or your university or your organization decides they want to do an on-site trial, we have all of our partners in the room here today. Citrix, VMware, Cisco, HP, IBM, here to help you do that. But the great thing about the cloud, it can not only bring you one GPU, but sometimes one GPU isn't enough. So with our iRay visual computing appliance, we can bring you tens of GPUs or even hundreds of GPUs to use in very advanced type of rendering. So now I'd like to welcome my second guest from Honda. Please welcome Mr. Daisuke Ide. Welcome.
はい、こんにちは。ホンダ技術研究所の井出と言います。今日は自動車のスタイリングデザインの評価のために、ホンダが独自に開発をしてきたツール、トップスについてご紹介したいと思います。今この画面に出ているのがトップスというツールになります。トップスは実機と同じ見え方を再現するためのツールとして開発を進めてきました。よって今出ている絵は、これは写真ではなくて、今現在リアルタイムで描画している結果になります。しかもここで使っている素材や環境といった情報は全て実世界のものを取り込んでおりますので、実際に物を置いた時の見え方を、例えばヘッドライトなど非常に難しい領域においても正確に再現することができます。じゃあ例えば、インテリアに行ってみましょうか。実はインテリアの計算というのは非常に光の計算が複雑になるので、膨大な計算量が必要となってきて、結果が収束するのにちょっと時間がかかります。今回は、実はその弊社で使っている 8GPU のワークステーションをこちらに持ち込んで、今そちらで動かしながら今デモを行っています。8GPU だとこれぐらいですね。でも実は弊社の中には 200GPU のスーパークラスターを実は投入して運用しておりまして、そちらを使うとこの今見ていただいている画面のだいたい25倍ぐらいのパフォーマンスで描画をすることができ、ほぼほぼリアルタイムの評価環境といったものを実現しております。じゃあまたエクステリアに戻りますと、そして驚くべきというに、こいつは全ての車載部品のデータを中に持っております。そしてトップスは自由に断面を動かして好きなところで評価するといった機能を持っております。例えばこんな感じで回してみたり、通常じゃなかなかお目にかかれないような見方なんかも自由に再現することができます。この機能とても面白いんですが、実は面白いだけじゃなくてスタイリングデザインにとって非常に重要な機能です。例えば先ほどのヘッドライトのあたりなどは非常に複雑に機能部品が重なり合っていますけれども、こういった内包の機能部品を意識しながらスタイリングデザインを完結させていく、こういった業務においてこのような機能はとても有用になっております。このトップスというツールはもちろん最新のレンダリング技術ですとか、それを高速で分回すNVIDIA の GPU テクノロジー、そういったものがあって成立しています。しかしながらそれだけではなくて、このツールというのは我々の強みである現場のスタイリングデザイナーが一体何を見て、一体どういうことを評価しているのか、一体実物で見るとはどういうことなのか、そういったものを深掘りしていった結果生まれたツールであると確信しております。今回はこのようなデモの機会をいただきどうもありがとうございました。Thank you very much, Mark.
Thank you.
Thank you.
So another amazing demonstration of NVIDIA technology. So in this short period of time, we've showed you how we've taken the GPU off of the desktop for graphics and finally enabled enterprises and in fact the cloud service providers to bring that back into the data center. But that's not the only place we're taking GPUs. You saw how the Honda car was designed on the outside and inside using GPUs. And next, I'd like to welcome Mr. Danny Shapiro, who's going to come up and talk about how we're putting NVIDIA-powered supercomputers inside the car. Welcome, Danny.
Thanks, Mark. Ohayou gozaimasu. It's wonderful to be here. Really enjoy coming to Japan, Tokyo, and being able to tell you a little bit more about what we're doing in the automotive industry. NVIDIA actually has been working with car makers for over 15 years. Virtually every single car on the market today was created using an NVIDIA GPU. The designers, in their early concepts, are using computer graphics, NVIDIA-powered workstations for styling and design. The engineers, as you saw from a CAD perspective, from a manufacturing perspective, they rely very heavily on visualization to be able to lay out all the thousands of components of the vehicle, to lay out the factory floors, and to model all this, again, using computer graphics and our GPU. Simulation, GPU compute is being used to do all types of work that usually would take days, weeks, or months and require millions of dollars. It can now be done virtually. So virtual crash test simulations, virtual wind tunnel simulations, virtual traction control studies can all be done interactively and iteratively to create better cars. We're also now moving GPUs, as you saw, into the cloud, but enabling the marketing and sales of cars as well. GPUs are able to do custom car configurators that can run on your tablet being connected to the cloud, or do virtual showrooms, as Audi is doing with their Audi cities around the world. Again, a virtual showroom that lets you design and customize your car. A lot of advanced technology, as you see, is being used in the design, manufacturing, production, and selling of cars. But now we're really excited to be able to take this technology and actually bring it into the vehicle itself. So NVIDIA, as you know, is well known as a computer company for creating a wide range of different types of products, from phones and tablets at the low end to laptops and desktop computers to servers and the cloud. High-performance computing, all based on a scalable architecture now. What we're doing is leveraging elements of each of these platforms and creating a computer platform for the car itself. So the Tegra processor, as you know, is a mobile computer, and now it's actually a mobile supercomputer. What we've done now is built an automotive-grade module that's the Tegra Visual Computing Module. This is what's going into cars. Essentially, this is a computer that runs an operating system. It can run Android, it can run Windows, it can run QNX, and Genevian open source code for automotive applications. This computer then has a lot of software that NVIDIA creates as well as our automotive partners work on together. But the benefit of this module is that much like your PC that you can upgrade over many years, this module is something that can easily be updated in the vehicle. The next video will show you what we've done working with Audi. This is their MIB system, or their modular infotainment platform. What you can see inside is that Tegra visual computing module. This enables Audi and other customers we're working with, be it BMW, Tesla Motors, and others, to create these systems that have a lifespan that can be extended through software updates, but also potentially by updating the hardware. In addition, since the automotive industry tracks its life cycles much longer time frame than consumer electronics, this strategy gives automakers the ability to more rapidly increase the frequency with which they update their technology. Essentially, each model year, Audi is able to introduce a new technology platform that has greater and greater capabilities. The car you saw out in front, the Audi S3, features this new system, an advanced infotainment system. If we go back to the slides now, we can see sort of the progression, in this case, what Audi is doing in terms of applying multiple generations of Tegra. The infotainment system was the first step, but now as we develop more capable processors, advanced SoCs in our Tegra line, it's being leveraged for more and more computing inside the vehicle. The TT is the new sports car from Audi coming out next year that will feature an all-digital instrument cluster. This will be powered by Tegra 3. they've also introduced a very complex and sophisticated rear seat entertainment system that will be based on Tegra 4. This will be the world's first automotive-grade tablet designed to dock in the vehicle, communicate with the vehicle, but also be able to take it out and use it as a normal tablet. And then the Tegra K1, as was announced at CES, will be used by Audi in their self-driving and piloted vehicle. Again, a lot of different applications, all based on the same Tegra architecture family. As we go back and look at now the state of the art in terms of graphics inside the car, NVIDIA is uniquely positioned to bring all the wonderful graphics research that we've done across all the different industries and types of things we'll hear about later today, and actually concentrate it and bring it into the vehicle to give the drivers and passengers a much better experience than they've ever had before. On one side, you'll see the virtual cockpit, the instrument cluster from the TT, which again is fully dynamic, can be personalized, customized as the driver wants to see things, but also changes for a context-aware situation. When you don't need a big speedometer or you don't need the tachometer, those can shrink down and display navigation, for example. On the right side is the Tesla Model S. It, in fact, has two of the Tegra visual computing modules, one driving an all-digital instrument cluster, and the other driving a 17-inch touchscreen. Tesla has done something that no other car company has done, and they essentially removed all the buttons, switches, and knobs and replaced it with a touchscreen that, again, enables the driver and the passengers to access a lot of different information and customize their vehicle experience. In addition, being a connected car, this system can be updated over the air, much like your phone or tablet. So we're seeing the automotive industry, along with NVIDIA as a technology partner, really able to mirror trends in the consumer electronics space. From a graphics perspective, though, what we want to do is really leverage so much of the wonderful research and development we've done, along with you, to bring these capabilities inside the vehicle itself. Recently, we introduced a technology called the material definition language. And what this is a very advanced way of rendering, not just doing basic OpenGL, but instead using the compute horsepower of our GPU to actually simulate how light behaves in the real world. Many different types of materials are comprising objects that we design, build, and buy today. What we wanted to be able to do was render how these different types of materials look. On the left side, you can see an example of how car paint is actually created. It's not just a single application of paint, but actually many layers. And so what we do is we render a base layer and how light would behave when it interacts that base layer, and other coatings. There might be metallic flakes. There might be a gloss coat or two. And so we're actually simulating how photons bounce around in the atmosphere, how they react to the actual materials. And as a result, on the right side, you can see how we can render a whole range of different materials. Now, this is something that goes on all the time in the worlds of visual effects for movies, or even the beautiful renderings of cars that we do when we're trying to create a photorealistic picture. What we want to do now, and we are demonstrating, is the ability to bring that kind of visualization inside the vehicle and create a much richer experience for the driver and passengers. So this next video shows an example of a three-dimensional object, in this case an instrument cluster, being rendered with this technology, the material definition language. And here I've rotated it to show you that it's actually a three-dimensional object. We can do very high resolution rendering, high frame rates, so you get very smooth animation of the needles. And then we can actually change the kinds of materials that are inside that vehicle, render something that's chrome maybe, or titanium, or carbon fiber. If we switch to the next video, it'll show a clip of a user interface that potentially you could use on your phone or tablet to actually customize your own car. And here you can select, do you want a powder-coated material? Do you want some form of metal, brushed or hammered? Do you want it to be copper? Do you want it to be platinum? The list just goes on and on. But we see the trend as people today customize their mobile devices, their phones, their tablets. The desire to be able to personalize your vehicle and have a unique look and feel will be very popular. So let's switch back to the slides now, and we'll talk about how, again, advances in supercomputing are really affecting the driving experience. Our goal is to make car rides more enjoyable, but even more important than that is to make them safer. Our technology, along with all the other sensors that are being put into vehicles, are going to reduce the number of accidents and fatalities on the road today. Now, it's quite astounding. There's over 1 million people killed worldwide every year in car crashes. In the United States, that number is about 34,000 people a year die. I was doing research. The number actually is very impressive for Japan. It's less than 5,000 people die annually, but that's still 5,000 people. Ironically, part of this research unveiled that every year about 14,000 people in Japan die in the bathtub. So I'm not sure what's going on in the bathtub, but maybe that's a topic for another GTC and a problem we can try to solve. But 5,000 people a year in Japan is still way too many. What we want to do is use computer vision, use what we call sensor fusion, the ability to bring a lot of data in, analyze it, and reduce the number of traffic accidents and fatalities. The types of features that we're starting to see on vehicles now based on these systems include pedestrian detection, blind spot monitoring, lane control systems, cruise control that actually adapts based on what's in front of the car. What I'd like to do is show you an example of a computer vision-based system that we've been developing along with a partner named Kashanti. So let's roll the next video. And what we can see here is the output from a front-facing camera being fed into one of our Jetson development kits. And what we're doing is analyzing all the frames of video, doing computer vision, basically detecting objects, tracking those objects, and then we can calculate what is the speed of our vehicle relative to the other object, what is the distance from our vehicle to that object, where are the lane markings, what are the street signs. And we can basically then become a brain that is the co-pilot to the driver. We can actually figure out what's going on around the car and alert the driver or potentially control the vehicle to avoid a potential hazardous situation. Let's go to the next slide. There's a huge amount of computation going on here. Many layers, and this is part of the VisionWorks toolkit. Again, CUDA is enabling computer vision to operate in real time here. Essentially, what we're doing is 3D graphics in reverse. We're taking data, in this case maybe video, that's two-dimensional data coming in. Then we have successive frames. So we can run different algorithms, like structure from motion, for example, where we're able to detect what's moving and also get a sense of depth. So we can detect features in these scenes. We can then track them using our machine learning capabilities, understand what those objects are, and then actually build a three-dimensional scene of what these sensors are taking in. So the next video shows something that we've demonstrated with Audi. And in this case here, what you're seeing is a side-facing camera. As the car drives by, it's looking for a place to park. What the camera senses, again, is just video. What the GPU is then doing is interpreting that video, creating a sense of notion of what is near, what is far, what is an object, what is not, and building these 3D fences. Then when it detects an opening, it's able to then sense that and will signal a place to park has been found. Again, this is all great stuff. It's all working in the labs. We have Nissan announcing autonomous vehicles. We have BMW, Audi, and many others really working on this. What we're really excited to be able to discuss with you today, though, is something that Audi showcased initially at CES, demonstrated at the last GTC that we hosted in San Jose, and now will be going into series production. This is something that the code name is ZFAS, and what it is, again, is a piloted driving system. In the past, it required 4 large computers in the trunk to be able to process all the sensor data on coming into the vehicle. What the system would do, though, is be able to detect other vehicles, maybe on the highway, when there's a traffic jam. The driver can turn on traffic jam assist. The car will then stay in the lane and maintain a safe distance to the car in front. So essentially, it's driving itself. The driver can take their hands off the wheels, take their feet off the pedals, and not have to worry. Then when the traffic dissipates, the system turns control back over to the driver, and they take over. Another mode, and it's very exciting, of how this will be implemented is in self-parking, where the driver can actually get out of the car, press a button on the key fob, and the car will go into a parking lot, find an open spot, and park itself. And then when you're done, say you're leaving a conference, you press a button on the key fob, and the car is going to come out of the parking lot and pick you up where you left off. Now, the image on the left isn't practical, but with Tegra K1 now, Audi is going to market with a system that will fit in the trunk of the vehicle, that will, again, enable this traffic jam assist, self-driving, as well as the self-parking. So there's a lot of great advancements going on today. The GPU is at the forefront of automotive. Wait, sorry, getting a text. Oh, looks like my car's out front. Have to go. Thank you very much, and I'd like to please welcome back David Kirk.
Thank you very much, Danny. That was really exciting stuff. I can't wait till my car can do all those things for me. So now I'm going to talk about the future of GPU technology. I love talking about the future because it hasn't happened yet, so we can imagine all the things that are possible. But I think one of the best ways to talk about the future is to start with the limitations of the present. So Aoki-san at Tokyo Institute of Technology has done a lot of really interesting work with GPU computing. And this particular work that I have the slides here for, he's analyzing performance with multiple GPUs to solve a computational fluid dynamics problem for weather prediction. And as usual, the work that he's done, he has a really deep understanding of what's going on inside the machine while he's trying to do his computation. So some of the problems that he's seeing represent bottlenecks in the system. In a modern PC architecture computer, there's some parts of the system that limit data movement and limit what you're able to achieve. The PCI Express connection between the CPU and the GPU is one such limitation. The memory capacity and memory bandwidth, particularly CPU bandwidth and GPU capacity, limit the amount of data that can be stored and the amount of data that can be shared between the CPU and the GPU. And what you see is, as you're trying to solve a problem and as you're scaling up the problem size, where you have more and more computation to do and you have more and more data to move around, these bottlenecks are beginning to limit your ability to effectively capitalize on the computational capability that is built into the chips. So these are problems that we'd like to try to go solve. So just looking at this in schematic form, the biggest limiter is the PCI Express bandwidth, which is very small, 16 gigabytes per second. CPU memory bandwidth is also relatively small. GPU memory bandwidth is very high, but we would still like it to be higher. You could always use more bandwidth. And the trade-off is typically CPU memory is large with low bandwidth. GPU memory is smaller with higher bandwidth. and communication between them is the slowest of all. So when you have collaborative computation where both the CPU and the GPU need to operate on the same data, you have contention and you have limitation because of the flow of data back and forth. So we introduced at GTC in San Jose NVLink, which is a technology for improving the interconnect bandwidth between the GPU and the CPU. The signaling is differential with a clock embedded in it, very high efficiency, low power, high speed signal. The programming model is the same as PCI Express with DMA, enhanced DMA kind of operations. And NVLink will support our unified memory feature, which was introduced with CUDA 6.5. And that feature allows all of the memory in the system to be addressed by either the CPU or the GPU through a unified addressing scheme. The first generation of NVLink will not be cache coherent. That'll be in generation 2, but you will still have the ability to share memory, both the CPU memory and the GPU memory. The speed of this connection will be 5 to 12 times the PCI Express connection at first, and we'll continue to scale that up over time. With all this additional bandwidth for communication, you can also use it for multi-GPU scaling. You can connect together multiple GPUs with multiple NVLink connections. And so then you can begin to think of multiple GPUs as a single logical GPU resource. And the unified memory feature underlying this allows all the memory that's directly connected to each GPU to be addressed and used efficiently by other GPUs as well as the CPU. So it's really tightening all the connections between the various processors on a node in the system. We want to make sure that we are accelerating CUDA and GPU computing on a variety of different platforms. Ideally, we'd like to be CPU agnostic. We don't want to have to care which CPU is being combined with an NVIDIA GPU in order to create a heterogeneous computing platform. So we, starting with CUDA 6.5, we're supporting ARM64 for CUDA. And that is typically the most cost-effective and the most power-efficient solution, ARM with the NVIDIA GPU. Historically, x86 has been the workhorse of heterogeneous computing along with GPUs, a very wide deployment, but it is neither the most cost-effective, nor the most power-efficient, nor the most performant. The most performant CPU implementation that we'll support is Power CPU from IBM. And we plan to have full CUDA support as peers for all these different types of CPUs. So the other innovation that we announced is 3D memory. And for the first time, we will be building and assembling chips on top of other chips in order to build an integrated computing system with memory built into it. And that will allow us to have many, many more pins and much more bandwidth per pin and more chips, more area for more memory capacity. So many, many times the memory bandwidth, at least 2.5 times the capacity of memory. So we will get over the limitation of restricted amount of GPU memory. And due to our signaling technology, we expect to see 4 times the energy efficiency for transaction cost per bit. So if you look at the curve on your right, the solid line represents the growth in memory bandwidth using the conventional memory packaging technology. And you can see that the the growth was starting to level off. We're starting to see not only a limitation, but a slowing in improvement. And with the new 3D memory technology, we expect to move to the dotted line curve where we can begin to see much greater improvement over time. And sky's the limit. We can have much larger, much faster memories. So we can eliminate these bottlenecks. So NVLink for interconnection, 3D memory for memory bandwidth and capacity, and unified memory so that all of these resources can be addressed efficiently across all the processors. Those three innovations will be combined to build our next processor architecture. And as you probably know, we have a habit, and we prefer to name our architectures after famous scientists who have made great achievements that we are impressed by and we admire. And so we aspire to create great things as well. So this architecture would be called Pascal, named after Blaise Pascal. He was a mathematician in the 17th century, and he made many of his inventions and discoveries while he was still a teenager. He invented the mechanical calculator. He invented probability theory. Maybe he had a friend who had a gambling problem he wanted to help out. He described Pascal's theorem, named after him, which describes how if you pick 6 points on a conic section and connect them together with line segments, the intersections also lie in a straight line. This is a very widely used theorem in projective geometry. And finally, Pascal's law of hydrodynamics, which states that in an incompressible fluid, when you increase the pressure at one point, the pressure increases equally at all the other points. And this is used in hydraulics and many other kind of fluid mechanical devices. So truly an impressive scientist, and something we're proud to borrow his name for our next architecture. So what is this Pascal? So this is the Pascal computer module. I don't have one of these to show, unfortunately. There's only one, and Jensen has it. But we're going to build it. We're going to build a lot of them. This is the culmination of bringing together this NVLink technology, 3D memory technology, and it'll be a fully self-contained computing module with the GPU chip, CPU potentially, and the memory, the 3D memory packed on it. So it's very small, very computationally dense, a third the size of a current generation PCI Express card. So what will this be capable of? We expect with Pascal to be able to continue our tradition of exponential growth in performance. Although, as I mentioned earlier, for CPUs and many other kinds of technology, we've reached the end of Moore's law and an inability to continue exponential growth. But with the innovations that I've described and some other architectural features, we expect that Pascal will be able to continue this exponential growth pattern. And so what I'm showing here is the historical performance for single precision SGEM, normalized performance, and simulations for the projected performance of Pascal, showing that we'll be able to achieve very exciting levels of performance. So what you might ask, what are we going to do with all that computational capability, all that memory bandwidth, and this wonderful new Pascal system? Well, really, we'll bring the technology, and the rest is up to you. It's the expectation is that we'll continue the partnership. We'll build the substrate. We'll work with you to solve your problems, to invent new things, to create the future world. So let's work together and show the world what's next. Thank you very much.